In the previous videos, we saw something disturbing. Programs can access memory that they should not touch, and the system often does nothing. Buffer overflows, use after free, out of bound reads. The compiler allows it. The CPU executes it. So the question is simple. What if we could detect these bugs the moment they happen? That's exactly what AddressSanitizer or ASan was designed to do. AddressSanitizer is a runtime memory error detector. It was developed by Google and is now a part of LLVM and GCC, which are the compilers. ASan works by doing two things. First one is it modifies your program during compilation. And the second one is it checks every memory access while the program runs. So instead of discovering bugs months later, ASan catches or crashes the program exactly where the bug happens. To understand ASan, you only need to remember one idea. ASan watches memory. It surrounds memory region with special zones that should never be touched. If your program touches those zones, ASan immediately reports an error. For example, let's say we have a code and it shows stack overflow. We have defined a 8 size buffer and now we are copying 12 size string into this 8 size buffer. So clearly this is a generic stack overflow bug which we see, right? Normally the program might crash or might silently corrupt the memory, but with ASan enabled, the program stops immediately. Let me run this. So yeah, GCC, and we'll use the AddressSanitizer. You can see here in the commands also for this stack overflow. In the previous video, we saw the compilers runs with no problem and then execute this also. So that is the undefined behavior. But we wanted to see, can we catch the crash with this AddressSanitizer? So this fsanitize address command means that we are using sanitizer. So it is a part of GCC now. So we can use this. So let's see after running this what we will get. Okay, so some warning is generated, but can we run this? The output we got. If we run this, so you can see we ran this and we got the instant crash, right? Now ASan tells us three important things. What kind of error has happened? So you can see here clearly it is showing stack buffer overflow has happened. Then the second thing is where the bug has happened, where the bug is there. So you can see here this buffer memory access offset overflows. And the third thing is the exact stack trace, which you can see here, right? So these three things are showed by this ASan sanitizer, AddressSanitizer. Now let's take a different example, more critical bug, that is use after free. Yeah, we saw in the last video this also, like this is very critical bug, right? The memory is freed but the pointer still exists. Without ASan this may work sometime, right? Let's say without ASan we use this GCC and UAF and that will give the output to the result, right? See, no problem. We didn't get any warning or any crash as such. And if we run this result, then you see the value 4 is printed. We haven't defined any value 4, but this is an undefined behavior. Let's see what happens if we use the sanitizer command. Let's remove this and use this program code uf.cpp. Now this will generate the output. Let's run this output and see instant crash. You can see what is the exact error here: heap use after free, and where that error has happened, you can see here the error has happened here, and then you can see the stack trace also, the exact stack trace for this error where it has been crashed. So this is how AddressSanitizer works and give us the exact details where the error has happened and what is the exact error. And you can see the red zones also. It shows us the red zones and where exactly this use after free has happened. So this I'll explain in detail in the next videos, where we'll see this ASan in much more detail. For now, just understand, if we use the AddressSanitizer, then we get all the details of the error, which in general run with the compiler, which we cannot find. With the help of AddressSanitizer, we can find that, right? So ASan detects that the memory was already freed and immediately stops the program. Now, what makes this ASan so powerful that it can catches this kind of failure that our compiler didn't find? This is the general question which comes into our mind. The reason ASan is powerful is simple. It checks the memory at runtime. Every time your program reads or writes the memory, ASan verifies that the access is legal or not. If something looks wrong, the program stops. This turns silent memory corruption into clear and reproducible crashes. You saw how many details we got from running ASan into that same program where we didn't get anything from the compiler. Now ASan becomes extremely popular among developers. Projects like browsers, kernels, and operating systems use it during testing, because ASan finds bugs that normal testing never catches. In fact, thousands of security vulnerabilities have been discovered using ASan. But there is a catch. ASan is not a magic. It comes with a cost. Program uses more memory, and then they run slower also. Why? Because ASan secretly maintains a second memory map called shadow memory. We'll discuss more on this in the later videos. So this shadow memory is where ASan keeps track of which memory is safe and which is poisoned. Understanding this shadow memory is the key to understanding how ASan really works. So in the next video, we'll go deeper. We'll see how ASan maps memory and how the poisoning we talked about works, and how 1 byte of shadow memory controls 8 bytes of real memory. And once you understand that, ASan will feel almost like magic. And remember, we'll keep it simple.